All right, good evening, everybody. Now we start the serious part of the evening, apparently. The task is up to me. So it's a great pleasure for me to introduce David Awschalom, the speaker of tonight. David Awschalom is a condensed matter physicist, and actually he's one of the most successful condensed matter physicists that we have today. He pioneered the fields of spintronics and spin-based quantum computing. And in fact, his name is so much linked to spintronics these days that when journalists talk about him, they usually don't say David Awschalom, but they say Mr. Spintronics. And so that's basically David. Now, spin has indeed played a major role in David's career. And you can see also a central trend from the early years where he was studying many spin systems in small nanoscale magnets when he was working at IBM, up to the single spin regime that he's working on now, and he will tell us about in his talk. David got his PhD at Cornell in '82. Then he worked for 10 years at IBM. And in '92 he obtained a professorship at UC Santa Barbara. And during this time in Santa Barbara, he had a very successful 2 decades. And there he did the work that most of us actually know him from. Now, a few years ago, he decided to take up a new challenge, and he joined the brand new Institute of Molecular Engineering, and that's in his hometown of Chicago. Now, to characterize David's research is a bit difficult, but I want to point out one thing, or actually maybe 2 things, and they are a bit connected. And that is that throughout his career, and actually still now, his research is really characterized by a very strong vision and a constant search for new opportunities. And I've experienced this firsthand myself. In fact, my own career has been influenced a lot by David's vision. I will tell you how this happened. So about 10 years ago, I was near the end of my PhD, and I was looking for a postdoc position. So I visited David's lab to apply for a position. And that was at the time when David had just observed the spin Hall effect, and that was really a major event. It was one of the major scientific discoveries of that year, 2004. So I went there early 2005. And I saw his labs, and I basically found what I expected. You know, very successful scientist, so it's all very, very good setups. You know, cryostats, lots of lasers, expensive microwave and optical equipment, all to do this imaging of spins and semiconductors that he was famous for. Now, besides all the fancy setups, there was one kind of odd workspace, a bit tucked away in a dark corner of the lab. And there was one PhD student working on that setup. It was a very simple setup, a few lenses, small diode laser, and there was a small sample. And so David explained to me that this student was trying to image a single electron spin in a room temperature solid. Now that was kind of surprising. So I was told the solid was a diamond, and the electron was held in place by a defect in the diamond, called an MV center. Now, at that time, there were very few people that were actually interested in MV centers. And I want to make a public confession here. When I first heard about the experiments on MV centers, I was not particularly excited. And that's a confession for me, as you will hear in the next few lines. So, after half a year, I decided to join David's lab, and I started my postdoc. And this one graduate student with the simple setup, he actually left. And David advised me to take over his research. And I thought a bit about it, and indeed I did take over that research. And it turned out to be the best decision I ever made in my scientific career. Because right now, MV centers are among the best controlled quantum systems we have. And all the experiments are being done by really, I think about 100 groups in the world, are really at the cutting edge of quantum science and engineering. Now, David would not have been David if he would stayed with MV centers, and of course he was already looking beyond MV centers. Maybe there's something even better. And I think now in his talk he will tell us about some new pioneering direction in which he's looking for MV center-like defects, but then in different types of materials. So with this, I want to end the introduction, because I think David will explain actually everything in much more detail than I've just told you. And I would like to invite David to come on stage to give the lecture. And by telling him that I'm very grateful, and the program committee as well, that he went all the way to Veldhoven to give this lecture. And let's welcome David with a round of applause.
Whoa. Well, thanks very much. Although I'm disturbed to be introduced as the serious part of the evening. And I think I'm also disturbed to be called Mr. Spintronics, but we can talk later about that. But thank you very much all for being here. Thanks to the program committee for giving me the great privilege of being here this evening, and for the Science Foundation for also giving me this great honor to address you after a lot of alcohol, after your dinner. And, well, also a special thanks to all of you for hanging around after a very exciting and intricate day of listening to great presentations, great science. But then I realized, of course, you're all physicists, and this is a free dinner, I learned, so, okay, maybe not so surprising. But what I'd like to do for the next 45 minutes is talk a little bit about, as Ronald mentioned earlier, something that came as a great surprise to a lot of us that's changing the way we think about technology, which is to think beyond today's technology and think about using defects or problems in materials as an opportunity to build a new type of technology based on the quantum degree of freedom. So, as is shown here in yellow, the aim of a lot of this area is to try and really think about a new class of electronics based on the spin of an electron or a nuclei that could serve to operate either with or without charge-based electronics. And one of the things I thought that's useful to point out is that this is a challenge that's been put in front of a lot of us for over 5 decades. And I think a lot of you may have seen this quote from Feynman, which is remarkably prophetic and a bit humbling to show that he challenged a large audience of the American Physics Society in the late 1950s, a group like this one, to do a few things: to build computers with wires no wider than 100 atoms, microscopes that could view them, machines that could manipulate them, and circuits involving quantized energy levels. And it's remarkable. I mean, the science and engineering communities in the world have embraced this and have really met these challenges head on. And the last thing that he offered as a challenge to the group was, could you use quantized states for new types of information processing? And this was in the late 1950s. So it's remarkable. And we've hit this moment in time that I think a lot of us are familiar with. You use a laptop on your lap and it gets pretty warm. As you scale down the feature scale of today's electronics and the resistance grows, the heat dissipation with today's materials is formidable. 100-watt processing on Intel Pentium chips and 2 and 4 core processing, 16 megawatts per cubic meter. It's an extraordinary power density. And it's hitting the limits of where materials really can remain robust. And we have to think about what robust really means. And this is an interesting number. Google searches alone are using about 250 million watts per day. So those of you who are searching every day about yourself, maybe you want to keep it down a little bit, because it's a lot of power. Think about that every time you see how wonderful you actually are. So this pursuit of perfection has really driven our technology and the fact that we can craft silicon with really unprecedented precision. And Bob Keyes at IBM in the late 1980s made this pretty interesting plot where he looked at the number of atoms of material used to hold a bit of information as a function of decade. And it's amazing how this data collapses on this curve. You can see where the Pentium 4 chip sits, and it's hitting the point where we really are going to have countable numbers of atoms just in our classical technologies. And I'm sure we'll have a way of dealing with it, but it begs the limit: what are we going to do next? And how can we scale? So in the course of building technology, there are a couple of other numbers that I think are pretty impressive. And this is from Intel out north of Santa Clara. 5 billion transistors produced every second on their fab lines. So that's 20 million transistors per person on the planet every year. So that's a lot of stuff. This is being recorded, right? Okay. So we have a great fabrication facility. We can craft materials, we can make small systems, and we've really hit this drive of perfection to try and do this with as few defects as possible to make highly conductive circuits with transistors operating at high frequencies working very well, because we've managed to move lots of impurities and really make high purity solid-state systems. But if we take a stand back, it's pretty interesting. Mankind in general, has been driven for a long time to impose perfection and order on his environment. Well, women as well. It's interesting that this part of the room seems to find that particularly amusing. And if you look on the left as an example of hedges, and you look at the right as, say, a mangrove swamp, you can see nature has a different approach. nature actually embraces disorder and imperfections and actually creates a very sophisticated architecture by using defects and imperfections that surround it. And it makes you wonder, are we really taking the right approach? So that's on the large scale. If you look down at our electronics technology again, we see how order is imposed upon our circuits. On the left, we can look at another Pentium processor, and you see this nice rectilinear pattern, right, of circuits, both in 2 dimensions and also now in 3 dimensions, where we have pretty efficient machines that are working at the level of 100 watts of power. And yet, again, nature takes a different approach, right? We have a 3-dimensional computing architecture, our brains, that embrace different aspects of disorder and manage to do fairly advanced processing of information and pattern recognition at much lower powers, which in some sense is impressive and also frustrating. So can we do better? Can we somehow use a different technique to think about next generations of technology by copying nature and maybe embracing a lot of the things that we tried so long to avoid in the worlds of science and technology? And for a lot of us, at the end of the day, that means you have to build something. How many here are theorists? Oh, good. So most of you are experimentalists. That's good. That's good. So if we look at the length scales of materials, starting, say, on the centimeter length scale, where we see a bee on a lily here, scale down to a millimeter and look at the eye of a bee, scale down to the micron scale and look at bacterium on pollen, go down to the 100 nanometer scale and look at a virus, on a virus. And if we go down to the nanometer scale, we're at DNA. And what's interesting when we go to these very small length scales is we have to redefine what we think about order and disorder. At the length scale of nanometers, the misalignment or misplacement of a single atom dramatically changes the property of a material. It takes so little to impact significantly how a material behaves at this length scale. So the rules are different. And the rules of what we think about a robust technology are different when we get down to this nanometer scale. Quantum mechanics tends to dominate. And disorder changes everything. It changes all aspects of a system when we're down at this length scale. But is this a problem? So historically, it's been a problem. So historically, people have shied away from building quantum systems because it was deeply believed, right, that environment would have big impacts on quantum systems. It would generate uncertainty, irreproducibility, and how would you ever know in a quantum system that you could really have a reproducible, robust technology? That is, in a quantum world, how can we really be sure? And part of the issue is that it was difficult to do some very simple experimental tests in real materials to see if, in fact, it was a big problem. It's true. So what is a nice quantum variable? It's the spin of an electron. In our technology, the electron has a spin as well as a charge. It is, by its definition, a quantum mechanical object. And the problem was, all of us thought that very tiny changes in a state of a system would grossly impact the output. That is, if you think about some sort of structure or some sort of image you're trying to look at, a very, very tiny change in the environment maybe this will be helpful with your government agencies. Tiny changes in the impact on the system would have great changes in the output. So things that would look the same or sound the same, in fact, could be very different. So this was a concern. And you might wonder, how could you test this? So all of us know, in the case of magnetism, if you have a spin, it can point up or down. But at the level of single particles, the spin can also be in a superposition of states. It's a quantum mechanical object, right? Yeah. So it can be up or down in a superposition, and that's our quantum mechanical state that we can prepare relatively easily in solid-state materials and then do some fundamental tests. But the trick is to do this at the level of a single electron to do a very clean study. And that's what I want to talk about. And the reason that I think this is a fun topic to discuss, and I think it should be encouraging for the experimentalists in the room, is that it's essentially a story that's told from a series of accidental observations in the lab. And one of the first surprises in the mid-1990s, something that Ronald was alluding to earlier, is that in an experiment done in simple commercial wafers of gallium arsenide, how many people here have worked on gallium arsenide? Yes. Gallium arsenide has always been referred to as the material of the future. So these were experiments to put magnetic ions into gallium arsenide, and then there was a simple control measurement to take out the magnetic ions, look at commercial wafers just purchased online of gallium arsenide, illuminate these wafers with a polarized pulse of light above the band gap of the semiconductor, so that generates spin polarized electrons, put a perpendicular magnetic field, and just watch them process. Look at how long these puddles of coherent states should last. And it was expected they wouldn't last long at all. And in fact, what this data shows at low temperatures is that based on the doping density of these wafers, the spin lifetime, or the coherence time, can be either very short, quite long, or very short based on the doping. A complete surprise that in just commercial industrial materials you could generate quantum mechanical states, in this case billions of them, and they would persist. And not only would they persist, but if you put on a small voltage across this wafer, you could drag these puddles of quantum states 100 microns or so through the material. They were mobile. And this really caught people's attention at the time, because at that time, the mid-1990s, the feature size for electronic technologies were a couple of microns. So in these commercial wafers, you could create, transport, and read out quantum mechanical states of just plain electrons over length scales much bigger than that feature size. So people began to think, maybe it's not entirely crazy to think about the quantum degree of freedom as doing something novel. That was at low temperatures, and then just by looking at different materials, by going to wider band gap systems, all this physics was moved to room temperature. And it was moved to room temperature in unusual but still commercially available materials, zinc selenide and gallium nitride. How many of you work with gallium nitride? This is a condensed matter meeting, right? Yeah, so gallium nitride is a very important technology material that's used a lot in solid state lighting. At this time, when gallium nitride was first being made, it was riddled with defects, threading dislocations. It was really, I think the technical word is really a crappy material. And so people weren't using it for much. But despite the fact that it was really filled with defects, it was able to generate and sustain extremely robust quantum coherence. A very big surprise. So it made us realize we still didn't understand very much about generating and playing with quantum states in just standard semiconductors, and it was a very exciting opportunity. And as more and more of these experiments were done with groups around the world, it finally begged this issue. At the end of the day, you need to do very clean studies. You'd like to actually look at fundamental properties of a single quantum state, one electron, isolated, and start to see really what can you do with something like this? How robust is it? So the question is, could you find one C in millions of them and manipulate it exactly the way you want with a great deal of precision and a high resolution? And that was the challenge in front of a lot of us, and that's what Ronald was mentioning in his very kind words in the beginning. Can we do this in solid-state systems where, again, you probably know that to build a fab today for the next generation of device technology, you need to invest about $6 billion. So you better sell a lot of computers, right, if you're going to invest $6 billion and recoup your money. And it's getting harder and harder to justify that. And I think as a lot of you have been reading in the news, it's harder and harder for companies to build these types of fabs these days because it's not obvious how you're going to recoup this investment. It's a lot of money. So what do you do? So as Ronald mentioned, you look at different materials, and one of the most interesting things that came up a number of years ago was actually a material that's been around for a long time, which is diamond. And it's been around for a long time for a lot of reasons. How many of you have purchased a diamond? Oh, come on, more than that. I'm guessing a number of you will be purchasing a diamond. So the next few slides are actually pretty important. So diamond's a historically pretty expensive system from the Earth, and yet things have changed very recently because now it's possible to grow diamonds synthetically. And when this was going on, a number of magazines started to write about what you could do, and Wired actually at the time had a pretty interesting article, and they pointed out, in fact, it was possible down at the end of the day that you could have $5 a carat, flawless diamond made in the lab. And if you look at the bottom, it said synthetic diamonds are about to transform computing too. And there were some interesting remarks by Neil Stephenson, I don't know how many of you read his science fiction, about how a diamond-based technology could really change things. So people really began to think about different materials. And now you can grow diamond with chemical vapor deposition techniques, large crystals. It's expected the price of diamond is going to change substantially. So for those of you who have already purchased diamond, Well, it's the moment, really. And for those of you who are going to be purchasing diamond, there are alternatives. You can grow large diamonds. This is some nice images taken from the Carnegie Institute in the United States, where they're interested in growing very large diamonds synthetically for making high pressure cells to look at dynamics in the Earth's core. So you can really make quite beautiful materials now, and that means you can also dope them differently, much like semiconductors are doped with electrons. In this case, diamonds have different color centers, which means you can add impurities to change the colors of diamond. And the jewelry industry has gotten very good at naming these. And they name them with names that also tend to inflict higher prices on people. But at the end of the day, you're just adding more and more dirt into the diamond, and you're raising the price. So it's a remarkable business. Canary diamonds are filled with nitrogen. Blue diamonds are filled with boron. And more defects are generated, and now it's very popular to be able to purchase what are called black diamonds that are riddled with defects. And they're also the most expensive. So what is it about these defects that makes them so interesting, and what can we do scientifically with these materials that are readily available? And that's what I'd like to talk about. So today's silicon technology is based successfully on two states, two choices. Transistors are on a gate, or they're off a gate. So you have a 0 or a 1, using really perfect materials so the electron charge isn't scattered and it's stable in the device. An alternative is to think about defective materials. Materials filled with damage, with these defects, where you trap an electron so it's hard for it to move off the device. But what you can do is manipulate the spin of the electron. You can point the spin in different directions. And you can see the power of this idea that if you think about a spin as a vector where you hold the base and you let the head of the spin move all over the place freely, like an arrow, it will trace out the surface of a sphere. And every point on that sphere is a data point. And if you can read that, it means that a single electron spin can store a vast amount of information, not just a 0 or 1, but as much information as you can read on the surface of the sphere. So it's a very attractive idea to have another type of variable in technology that could have big impacts, not just in quantum processing, but also in storage. So how do you approach that? Well, you get a piece of diamond, and you look for a defect. So some of our students worked on making this very nice movie. We just had the Golden Globes. So you take a diamond, either a natural diamond or one that you grow synthetically, and you start to look inside the diamond for defects. And if you look inside a diamond, we know diamond is made of carbon, which you can see here in blue, in a very nice lattice. There can be some impurities in it, which are shown here in red. And once in a while, you'll have a missing carbon atom or a vacancy, which you can see here sort of glowing in white, which is near one of these dopants, in this case nitrogen in red. And the so-called nitrogen vacancy center that Ronald alluded to earlier, when you pull out the missing atom, you tend to distort the lattice and create a type of molecular state that holds essentially a single electron. And this electron begins to process it, has a spin that can move at a certain frequency, and you can manipulate it either by illuminating it with light or by applying magnetic fields. Pretty much just like that. You take a magnet and you move it in and out. And you have a very nice quantum object on the desktop that you can play with, something that would have been very difficult to imagine, just a decade ago. So in this way, we'd like to think about these materials very differently. So we'd like to think about these semiconductors like people. It's the defects that make them interesting. And admittedly, some people are more interesting than others. But let's talk about this defect. So I apologize, I have just a couple of technical slides in a few spots here. I know it's late. But one of the neat things about systems like this is that nature's been very kind to us, and it's created an electronic system that looks very much like a trapped atom. So we can follow in the footsteps of what a lot of fantastic atomic physicists have been doing over the last number of years, looking at individual atoms. In this case, you can think about the defect as being an atom trapped in this lattice. And the amazing thing is, as shown in this diagram, you can simply illuminate this material with light at a wavelength that takes it above the excited state. And the system will simply relax by itself through a metastable state into a ground state that, as you repeat this over and over again, called a cycling transition, ends up with a spin polarized electron in this ms equals 0 state. And all of that's done within a 5.5 electron volt band gap, which means this is very robust at room temperature. 5 eV is a very big temperature scale. So that's amazing. It means you take a diamond, you just illuminate it with unpolarized light, and you end up with a polarized electron. Now there's a second thing. In magnetism, you typically play with spins by a magnet, right? And so the Zeeman effect tells us if you apply a magnetic field to a spin system, you lift the degeneracy of that spin system, separating spin up and spin down with a magnet. In some materials like this, there's enough internal strain in the lattice that the strain in the material lifts that degeneracy for you. So it's another remarkable thing. You can address spin states without a magnetic field. And you can manipulate the spin up and down with microwaves. In this case, 2.8 gigahertz microwave radiation, which is pretty close to cell phone frequencies. So it's very accessible, relatively straightforward to do. And what this means is that you illuminate the diamond to orient the spin, you apply microwaves to play with it, and then you look at the light that comes out to read it out. A beautiful, clean, simple to test some basic quantum ideas. So what do? You go online, and you can go to companies like Sumitomo Electric and get a piece of diamond, a thin film of it, put it under a microscope objective, send laser light in it, scan the objective around, and you'll get an image like the one in the upper right here. So you see those bright spots. The bright spots are these individual defects. And if you look a little more carefully at the image, you'll see some dimmer spots lying around. Those dimmer spots are defects below the focal plane. So they're all over the material. So you can hold your microscope objective over just one of those defects. And so if you look at this image on the left side, you'll see there's a green laser beam that's going through the objective that's exciting this defect. And then the light that comes out in red is split into a pair of single photon counters. And if you have a single object producing a single photon, that photon has to decide if it's going to go to one detector or the other, but you know it can't go to both at the same time. So you can do a correlation study, and you can prove to yourself that, in fact, the photon has to choose a detector. It's a single object producing a single photon, but is it a single spin? And the way to be sure it's a single spin is to apply this gigahertz radiation. Make the spin flip between up and down with a wire. And these early experiments were done just with a wire. And if you do that, you get data like this one that shows the change in the luminescence light as the spin goes between up and down. So this looks, for those of you who do electron spin resonance, this looks just like ESR. But this was a pretty big defining moment in our field of spectronics because this was something that people have been trying for decades to do. Measure a single spin at room temperature with no magnet and do it in about 20 minutes. And that's what these materials now enable you to do. So that really changed the landscape of thinking about spins for both quantum information processing, for possible memory applications, and maybe you could use quantum mechanics as the basis for new technologies for both processing and, as you'll see, for sensing and also perhaps for imaging. This is not a picture of Ronald, but it's a picture from Ronald. Just to emphasize again that all of this work is done at room temperature. That's a big change in the field. So for those of you who have purchased a diamond, and those of you who are clearly afraid to admit you have purchased a diamond, when you go into a store, diamond is typically has a value based on the 4 C's. The color of the diamond, its clarity, the carat, and the cut. For spin-based technology, we're going to use a different set of C's. We're going to see how coherent is the state, how well can we control it, can we communicate from state to state or over global sets of states, and can we couple into the real world in different ways? And I'm going to walk you through some relatively recent experimental results that show a lot of these results I think are pretty surprising. It turns out that these defect-based systems have remarkably long coherence times. They can be used, you can have very high degree of control, you can communicate nicely with them, and you can couple them. And in a way, it's a little bit embarrassing to talk about some of this work here because I think many of you are familiar with the extraordinary accomplishments in this area that have been going on in the last few years at Delft with Ronald's group that have really been pushing this science closer and closer to a practical technology. Really extraordinary experiments. So one of the things that we're very fond of in our own research is can we think about looking at this physics mindful of the fact that we will have a technology someday. And if you look at how the world of semiconductor technology has developed transistors, they have to be able to put dopants to build devices in very specific locations. And the way that's done in industry is to make a bunch of holes in a mask, shoot ions through those holes, and put dopants in where you like, through a mask. So we did the same thing. We made masks on top of diamond. They're on tens of nanometers or so in diameter, and sent these to commercial companies that would shoot nitrogen ions through these holes. In our case, trying to systematically damage the material, create these defects, and put these spins in very specific locations. And if you go through a process of doing that through these commercial vendors, it's about a couple of day turnaround. You do this, and sure enough, admittedly not in the most successful way, but you can make a variety of 1, 2, or 3 spins in different locations in big arrays, and actually build quantum states on demand. And for those of you that are technologists, one of the cool things about this is that there are very few examples in the technology world where you can build a system from an individual electron, say in the top left of that letter U, to the macroscopic length scale, tens of microns, all on the same chipset. So you have an incredible length scale that you can begin to operate and think about architectures of new types of technologies, from individual electrons to atoms to tens of microns to large-scale metallic systems, but all in a single level. It's very, very unusual to be able to do that. So what can you do with that? Well, you can ask a couple of fun questions from technology. So every time you try and buy a newer and newer Pentium chip, it's a couple of gigahertz, it's 1, it's 2, it's 3 gigahertz, then you don't see much change. And one of the questions you might ask is, how fast can you move a single spin? So this is an interesting issue in technology because there are lots of techniques to see how fast you can move charges on transistors, but they've been limited to tens of thousands of charges, not one. It's very hard to find examples of single charge electronics for logic. It's a very difficult thing to do. But here we can take a piece of diamond, that yellow chip that you see, put on a small waveguide structure that's made with titanium and platinum gold, all put on diamond, try and make it as expensive as possible. Pick a single spin that sits in there and see how fast you can manipulate it. And it turns out you can manipulate it very, very quickly. Hundreds and hundreds of megahertz with no problem, gigahertz no problem. And there's an example of one such spin in one of those waveguide structures that was controlled, and that's the data you see in the middle of the screen. And it's a very interesting result. That's an entirely useless device. But it does tell us that you can move a spin between up and down on the same time scales that's in today's SD-RAM technology, say in this Lenovo laptop. So it's also a very interesting result then, right? You can move a quantum mechanical object without moving its position, right? You're changing its quantum state on the same time scale that's in our state-of-the-art charge technology, but at the level of an individual electron versus tens of thousands. So it's not crazy anymore to think about developing quantum mechanical systems based on solid-state materials that could be used with very different types of functionality. So I have just 1 or 2 other examples I wanted to talk about before we move into some applications about what sort of neat things you can do with a system like this. And with these so-called nitrogen vacancy centers, everywhere you have an electron spin, you have one of these nitrogen impurities. Now, the nitrogen atom has a nuclear spin. So if you can control the interaction between this electron spin and this single nuclear spin in the core of the atom, you can think about that nitrogen atom as a single quantum memory, a nuclear memory. Nuclear spins have very long lifetimes compared to electron spins because not many things bother a nuclear spin. It's pretty stable. They can have very long lifetimes. And in physics, most of us know that there's a hyperfine interaction that couples the electron and the nuclear spin. So if you can control that with electronic gates, you could actually transfer the quantum state into the core of an atom, come back later and extract it, and actually have a single atom memory, where that single atom, as I mentioned earlier, could have a very high density of storage. So that's the idea. You have a single electron spin in blue. Right next to it, you know, by definition, there's a single nuclear spin in purple. And if you can control the way those two talk, you have a local memory. And so that was done. And it was done in the sense that you could actually demonstrate taking some of these large arrays made in diamond by putting in defects. You pick one. You try and move information between the electron and the nuclear spin. And this data in the bottom left shows the electron spin lifetime highlighted in yellow The red curve is the single nuclear spin after the information is transferred into the core. And then you come back later and can extract it. So this was a nice demonstration that, in fact, as a proof of concept, you can build a single spin nuclear device. It works really badly as a practical memory. But more recent work using a modified version of this technique actually took these lifetimes to seconds from the shorter times in these measurements, and those times keep improving. So we very much believe there will be single nuclear spin memory devices which can be used as a local resource for new types of technology. And I think it's hard to imagine just 5 or 6 years ago, if you were asked to build a single nuclear spin subatomic memory that could be addressed with one particle, people would think you were crazy. And now you can do it on the desktop. All of this, again, just under ambient conditions, everything at room temperature. It's quite remarkable. In this case, this memory operated at speeds of 120 nanoseconds. So it's a pretty quick device. You can transfer information pretty quickly and take it out again. So what else can you do with something like this? I've talked a lot about memory, things about logic. I want to be mindful of the time because I was told the bar opens later. All of this work was done by looking at quantum states built inside a material. Now, what happens if you can take them off the material and be able to move them around? And so a lot of people in the world have been thinking about building quantum sensors. So on the left is an image of taking some films of diamond that were grown synthetically by chemical vapor deposition in our own laboratories, etched into small pillars over a wide range of sizes and shapes. And if you look at the drawing on the right, sorry, the SEM image on the right, it's definitely not a drawing, a little jet-lagged. You can see that these small diamond pillars are weakly attached to the surface with small polymer threads. And the idea is that each of these structures have either 1, 2, or 3 quantum states in them. You release them by putting them in an ultrasonic cleaner, effectively, get them in solution, pour them through filter paper, and you end up with these little quantum probes, each spin engineered with a couple of quantum states. And you could take these probes and use them. So there's a blow-up of them. And so what are people doing with these types of probes? Well, a group in Australia has done some beautiful measurements shown in the bottom right, where they've actually put quantum probes inside live cells, these HeLa cells, and used them to measure electromagnetic fields in the cell. And apparently the cells are very happy having consumed the diamond. I've told my graduate students it appears perfectly safe to eat diamonds. And they seem to be doing fine, even though they're not here with me today. One of the interesting things that came out of these measurements that students were doing is when they looked at a particular set of quantum probes every day, they saw that in the way we were doing this particular measurement, that there was a little bit of a change in the frequency every time they measured. And at the end of a couple of months of looking at this carefully, they discovered that, in fact, the quantum mechanical wave function, if measured in a certain way, was incredibly sensitive to temperature. So the students came and said, this is a disaster. I said, no, the beauty of physics is that one person's disaster is another success story. That's not a liability. That's now a quantum thermometer. And in fact, it turns out they're extraordinarily good thermometers. You can see a part in the 10 to the 5th at room temperature just fine with these quantum probes. And when we talk to some of our colleagues in the world of bioengineering, they're teaching us a lot right now. And one of the things they've been pointing out to us in a lot of biological processes, and I'm barely speaking to the edge of my knowledge here, it's very important to be able to do a precise temperature measurement at a very specific location, say on both sides of a cell wall, where a lot of processes are believed to be driven thermodynamically, maybe not with chemical potentials. And it's been very difficult to do very good local nanometer-scale thermometry. So by functionalizing these outside of the diamond and allowing them to stick in certain positions, there's an opportunity now to do very localized nanometer-scale thermometry based on the quantum state of a particle. I think a type of probe that, again, a few years ago would never have occurred to any of us to use quantum states as thermometers. But now there are a number of emerging applications where nanometer-scale thermometry, in principle, could play a very important role. Now, what else could you do? If you want to look at molecular systems outside a surface, and this is a topic that's up for debate, but a number of people in this field of quantum information are beginning to believe that one of the biggest impacts of quantum state control in semiconductors may not be quantum computing, but maybe quantum sensing in the sense of trying to do magnetic resonance imaging. You know, it would be nice if you could look at individual proteins, for example, without the needs of crystallization. So there are a lot of proteins, right, where the structure-function relationship is poorly understood because the proteins don't crystallize. So it'd be awfully nice in a perfect world, in the future, in principle, if you could have proteins in solution or a particular molecular species you're interested in and understand its structure at the single molecule level using magnetic resonance imaging. So that's a daunting goal. There are a lot of challenges to make that work. But in the last 2 years, groups around the world, groups here in Stuttgart, groups at IBM Almaden, working with our own laboratories, have been pushing to see, could you look at protons, external protons with quantum probes? And these are very small signals. And I just want to show you a quick example that about a year or so ago, I was able to, a couple of groups in the world were able to detect external molecules, nuclear spins of external molecules with these individual electronic states, and more recently done two-dimensional imaging of single molecules at room temperature. So for those of you who do magnetic resonance imaging, this is not an awe-inspiring result, perhaps. As one of our program managers said after seeing this result that we were really excited by, he said, and I think I'm quoting him, "It looks like a blob." And it does. But it's a nuclear blob. Yeah, at room temperature, with a 12 nanometer spatial resolution and a 200 nanotesla squared vertical amplitude. So it's a big step in resonance imaging at room temperature at the molecular level. It's nowhere close enough to do what we'd really like to do. But given that a lot of this work has been driving in just the last 3 to 4 years, I'm pretty optimistic that people will become a little bit more clever in their pulse sequences and with the molecular engineering to be able to actually get this to work. And I think when it does, it will have big impacts in fields from bioengineering to biochemistry to broad areas of the physical sciences. So we're very excited about this direction, and we'll see how well it goes. But in the remaining 5 or 10 minutes I've got left, I want to touch on the subject that Ronald mentioned earlier. So a lot of this work is going with diamond, and much like high temperature superconductivity and other areas of condensed matter physics, you might ask, why does this work in diamond? And diamond can't be the only material on Earth where this works. And our own group developed a collaboration with a group of theorists trying to apply density functional theory techniques to do a type of genetic screening, to look at different materials, set up some parameters, and calculate from first principles, is it possible to identify different types of structures where if you pull out an atom to create a defect, you could also trap an electron and build quantum systems. And after running for about 1.5 years, different types of code, the Chris Vandewalle group in Santa Barbara, with some help from our students, predicted these first 7 different materials I'm showing you here. And what was striking about these predictions is that all of these materials are commercially available. And the one I want to show you, the first one is silicon carbide. And silicon carbide is a very well-known, highly productive, high-power electronic material that's used a lot in avionics. Those of you who've used a hot plate, if you typically use silicon carbide sensors in it, it's a semiconductor that works at elevated temperatures, and you can get large scales of this material pretty easily. And there's been a long history of trying to make non-volatile logic. Here you can see from the mid-1990s, people have crafted pretty sophisticated integrated circuits, and still do, with silicon carbide. And one of the attractions for us, of course, is that when you grow diamond, you typically are dealing with very small substrates. When you use these other materials, you can get 4- and 6-inch wafers. And for those of the graduate students in the room, you can appreciate how much nicer it is to have 6 inches of material versus a few millimeters, particularly if you were to lose your sample, say, in the processing areas of the clean room and have to explain it to your advisor, who spent a lot of money on this sample. Not that I'm bitter. So there's been a lot of interest in driving high-power electronics, and in the US, President Obama recently announced a large-scale investment program. $70 million may seem small, but it was matched multiple times by industry to end up with a several $100 million program to push wide bandgap electronics for both photovoltaics and high-power electronics technology. So there's a growing interest in systems like this, and in a lot of areas. So I mentioned you can make high-power electronics with silicon carbide, like power MOSFETs, which you can buy online. Silicon carbide is used for MEMS devices, for making mechanical actuators, both for airbag deployment systems, for mechanical sensors. And again, I'm sure many people here are familiar with the fact that you can flash silicon carbide to make graphene for a lot of structures. So it's a very flexible system. And let me just show you what happens. If you repeat the experiments I talked about for the last half hour or so, in fact, the theoretical calculations were right on target. You can generate quantum states in these commercial materials. Some of them exist very nicely to room temperature, but there's one other nice aspect of these states when you change the material. The wavelength of the light that's used to play with them is all in the telecom region. So now you have a commercial material where the spins can be manipulated with telecom wavelength photonics on industrial level substrates. So when there is a lot of material, there are a lot of things you can do. And silicon carbide has one other feature, which a number of semiconductors have. It comes in different forms called polytypes. Now, so how many of you know what a polytype is? Okay, so you know it's not a social disease. So a polytype means that you have a crystal where the order of the XY plane is the same, but as you change the growth conditions, the Z spacing can be different from crystal to crystal, and you can control that. So as you build a crystal where the Z-axis can have different spacings, it also means they have different band gaps, which means you can build very interesting structures at different wavelengths, such as quantum wells and quantum barriers, all out of the same material. And very recently, some of the students have shown, despite our intuition telling us that materials like this should be terrible for quantum information, because there are nuclear spins all over the material that should dephase these individual electron spins very quickly. Despite that, the spin lifetimes are extremely long. So we don't know exactly why that's the case, but it's good news that it is. And these different polytypes mean that the spins can be made in different orientations in the lattice, each one at its own wavelength. Each one can be driven quantum mechanically. And the state on the right are individual electrons, each one pointing in a different direction in the lattice, each one addressed individually, each one at a different frequency, all in the same system. So I'm showing you this because it just is a nice example of the wealth of science that comes out of understanding a basic process, exploring the world of materials and different handles to play with this process and tune it. And as more and more of this information comes out, more and more applications are emerging. So I want to end with saying, what are people now thinking about quantum materials and quantum systems? And the first thing, and probably the most prolific thing you read about, is quantum computing. And just when I end, I wanted to mention a few things. So some of you who may not work in this field appreciate why this is so tantalizing, why taking these individual quantum states that work at room temperature in semiconductors is such an important thing to be working on. So for those of us who buy computers today, right, all of us, we want to build a more powerful computer. What do? If we take an Intel Core i7 CPU chip, right, a pretty recent Intel processor, there are 4 cores, there's 700 million transistors in that Intel quad-core chip. A lot of devices. So how do you double the power of that chip? Yeah, you buy 2 of them. And roughly speaking, when you buy 2 of those chips and you put them together, doubling the number of transistors doubles the computation power, roughly. That's not entirely accurate, but it's pretty close. So that's our classical technology, and that works. Now, a quantum technology, which we're expecting Ronald to deliver, I believe you said that over dinner. Let's say you had a 10,000 quantum bit chip, so 10,000 types of transistors, and you want to double the processing power of your quantum chip. All you need to do is add 1 quantum bit, not 10,000, just 1, because of the exponential nature of the scaling and the fact that these bits are all entangled. The scaling is very different with a quantum machine. So what does that mean if you took 10,000 quantum bit chip and you added 10,000 more quantum bits? Right? You create a computer with 2 to the 10,000 times as powerful. So those of you that are like currently looking at your iPhone, you could I'm just saying. There are 2,000 people. I can do the statistics. If one of you has that available, you could tell us what 2 to the 10,000 is. It's a very, very big number. Very big number. You can compare it to the number of observable atoms in the universe. So 10,000 plus just 10,000, not 700 million, is a very big number. And this is part of the excitement of working on a new type of technology like this. And it's a little bit like Facebook. So quantum computers rely on the fact that information is stored in the relationships between these bits. Things are entangled. So adding 1 qubit doubles the number of relationships. If your child has 1 new friend on Facebook, you worry about it. Okay, we'll talk at the bar later. So what does that mean? It means that when you try and build these networks, every time you add a quantum state to this network of quantum states, you're developing relationships that you may or may not understand, but there are a lot of them. And if you can control this, you're doing a vast amount of processing of information in ways that would be very difficult to do with our technologies today. And that's one of the reasons that a lot of us are so excited here. If you could build machines that really did have extraordinarily computation power, you could think about simulating molecular properties from first principles. You could think about designing pharmaceuticals whose properties could be predicted from first principles by simply running these wave functions through the system. You could think about engineering new types of materials with unusual properties, and you could even think about impacts in areas like synthetic biology. So it's really fun to think about what you might do if such a machine really did function, and if we learned how to program such a machine. So there are a lot of challenges in this field, and there's a lot of excitement. So let me stop here and think about what does this mean for all of you, particularly the students in the room. I mean, I think a lot of us believe this is an extraordinary time in condensed matter physics. We're seeing this change from the classical world to the quantum world that's readily accessible by changing and playing with materials. We're also seeing a field where experiment and theory are working really closely together. I think in unprecedented ways. They really have to work together to drive this field forward. We're finally at the level where individual quantum states can be engineered, they can be connected, they can be manipulated with light, with magnetic fields, with electric fields, with photonics, in ways that are very powerful. And I think we have a largely unpredictable past when you look backwards, present, and I actually believe the future. But it is an opportunity for what we believe is going to be an emerging field of quantum engineering. And it's this unique environment, and one of the things that I'm finding extraordinary in the Netherlands is how it seems to me, as an outsider, the Netherlands is sort of uniquely developing this for various reasons I may not understand, but we're seeing the symbiosis of science and engineering and material science forming at the universities. It's a very powerful educational platform for students where I think the future looks very bright when I'm counting on many of you to both build and operate our future quantum machines. So thank you very much. Thanks for having me. Thank you.
Thank you, David Awschalom. A wonderful insight in the world of the very small, the quantum world, and how we can access it. Thank you once again. It was a wonderful pleasure. Yeah. And then there's this other hard task that I have on this evening. I have to pronounce the magic formula. The bar is open. Thank you.